This is my review of the OpenBuilds MiniMill, with the focus on how it does at cutting aluminum. It's something I was looking for specifically when I bought the machine, and I didn't see a lot of reviews out there that showed aluminum cutting that was more than just grinding away slowly at little bits of dusty aluminum. So here's what the MiniMill looks like. The kit came. I had some experience from building 3D printer kits, and this was pretty easy to put together. It's a lot of the same technology: lead screws, stepper motors. Here's the X and Y axis together. And here's my build of the Z axis. It has a slightly different arrangement for the little wheel bearings that run in the interior of the C-beam instead of the exterior. Here's the full thing together. The electronics, I have my 24 volt power supply there. I have an Arduino with a girdable shield and a little breadboard there that I use for breakout, and a fan runs on the 24 volt to use for cooling. Originally, I had these set up like you see here because that's how they showed it in the their assembly. But I realized really quickly that having them here was a bad idea when you're cutting aluminum, because at the speed that this router spins, 16,000 RPM and above, the aluminum chips really go flying, and they will fly everywhere, including into these electronics. And I actually had it short out one of the stepper motor leads on this breadboard. Luckily, it just shorted that out instead of shorting out something in the power supply. For the software, I use BCNC, and this is just setting the G code to the Arduino running Gerbil. I found this to be fine. It has some auto leveling, which helps with PCBs. I haven't found anything better as a G code sender. This is what it looked like after I put it all together and added some 3D printed parts to use as mounts for the bellows that keep the chips off of the lead screws. I also had to print a little adapter for the Makita router that I used because it was a little smaller. The diameter was smaller than the diameter of the Bosch router that it comes with, or that it is shown with. I picked the Makita because it kind of looks cool. It looks a little more sleek, and I've actually found it to be a really fantastic router, so the run out is extremely low. The other thing I did was I built an enclosure around it. You see here, it's just something that was built very quickly out of some sheets of acrylic on the back, front, and top, and then MDF on the sides, and some just 1x1, I guess that's 2x2 for the frame. So when I was trying to decide how to do the first cut, I looked at the rating on the router, and it's a 1.25 horsepower router. And I looked at the actuator test data that OpenBuilds supplied, and they said, hey, with this lead screw, with these NEMA 23 stepper motors, which are the ones I used, the ones that you can optionally get with it, the motor stalls at a 26 pounds of cutting force. So I was like, okay, so let's design a cut for those parameters that should be very conservative at first, because I want to make sure that I'm not stressing the machine. So I set the radial width of cut, axial depth of cut, 0.05 and 0.1 inches. And if I looked at the computed values, the power motor, very, very low horsepower. Maximum force vector is also fairly small, 1 or 2 pounds compared to the 26 pound stall. Figured I was, less than 10% there would be absolutely fine. And here's what it looked like the first time I took a cut. Luckily, I had an e-stop wired up, so I was able to hit it and turn everything off really quickly. And trying to figure out why this happened, I think it has to do with the weight and rigidity of it. If you look at simple, like this is a very lightweight, very inexpensive mill, and it's 175 pounds. That's the shipping weight, I think. I think the actual weight of the machine is more like 100 pounds or so, but still, that's like 10 times as much mass as the MiniMill, the OpenBuilds MiniMill. So all that mass does a lot for damping and rigidity, and I just think that it was a little too much, so I cranked the axial depth down to 0.05, so hopefully half of the cutting forces and horsepower required. And this is some early cutting I was doing. And it's kind of able to get through it. It doesn't sound great. And there's it's fairly slow, but it can definitely create some resonances. Here's an example. Not only can you hear it, you can actually just see the camera vibrating. And here's what the finish looked like after my first few cuts. You can ignore the little knurled looking part at the angled part. That was a weird intentional finish that I was kind of fiddling around with. But what's important is around the edges, you'll see it kind of looks like a bunch of nickels stacked up. And that's indicative of the kind of finish I was getting, which was just not very good. I think that's, as the machine was vibrating, the head of the cutter was bouncing around and causing these marks. Here's another example of some horrible vibration problems. Skipping ahead a little bit, you can kind of see from this view just the finish is not great. It's not just being able to see the swirls, but also just seeing the kind of stacked up nickels. So here's what a 1/8 inch end mill does, and it's better. It still doesn't sound great. So it's a respectable cut. The other thing I tried was some PCB engraving. So I used a 20-degree V bit and engraved using the auto leveling feature in BCNC. Basically isolation routed some PCB test lines here, and you can see that 8 and 18. That's 8 mils trace width out to 18 mils trace width. Mils are a weird unit that are used in PCBs that means thousandths of an inch. I don't know why, but yeah, so that's 8 thousandths wide, and the quality here is actually really fantastic. That's a US dime up there, and you can see the like the numbering and stuff. It's really clear. Like there's really no backlash or other artifacts that I'm seeing from repeatability problems. It looks great, and I cleaned this up a little bit and tested it for continuity, and it was fine. So I haven't actually created any working circuits yet, but I think it would be fine for that. The precision here is really surprising, especially from a Makita handheld router. I don't know why it's as accurate as it is, but it has extremely low run out. So in terms of actually making things, I had to go pretty conservative with the cuts. This is an even more conservative cut, so I don't remember what exactly the axial depth of cut here is, but it's pretty thin. And you can still hear it's not happy, but it's doing it. But this takes forever, and so I wanted to actually make pieces a little more quickly than this. Also, all that vibration does create some heat issues. and I'm sure it's dulling the tool. So the first thing I did is I tried to reinforce the column. You can see here just a piece of, I think that's 1/4 inch thick aluminum that I created bolt hole patterns for, and just tried to reinforce that piece of C-beam where there's a single piece for a length. And I have some video here of actually doing some testing of trying to move the column, kind of pushing on a little bit and seeing what the results are in terms of the movement. That's a thousandths dial, so yeah, like well over 5, almost 10 when I really pull strongly on it. 10 thousandths of give, which is not great. I was trying to figure out the reason for some of this stuff. I mean, certainly the frame isn't as rigid as it could be. The other thing I noticed is just these nylon wheels that run on the inside of the track. If you imagine the router out there kind of has a lever arm that will put a lot of strain on those, and I don't see that they have a lot of way to resist that movement. So what I did is I replaced that bearing system with just some linear rails. These are just MGN 12C cheap linear rails that I got off of eBay, and they fit on pretty well to the existing C-beam. And then I had to make a new C-axis plate. I also got a new a second mount for the router that's actually the correct diameter. And so here's both of those first upgrades together. So again, this is that same cut as earlier, now back to the 0.05 axial depth with those first upgrades. So it still doesn't sound great, but it does do a lot better than the original prior to these upgrades. So there are improvements here. It's still doesn't sound happy, but it's not vibrating as poorly as it was before, and this is with a decent cut. 50 thousandths is not huge, but it's enough to get through some parts without taking a huge amount of time. Trying to think about why there is still some vibration there, and like what's still causing a lack of rigidity. One of the things I realize is that I have this thing bolted down to a workbench that just has some plywood, 3/4 inch plywood, and that plywood obviously isn't offering any rigidity. It's just keeping the thing from moving around. So if you consider that, like the column, I reinforced that one part of the column, but really that bending and pulling on the top part of the column is actually going to cause the bottom to bow out, because really, in a way, it's like one big long piece of C-beam. So reinforcing the little bottom slides there doesn't really reinforce as much as I wanted. I have a little blue arrow trying to point to like, hey, look at this thing. It basically causes like half of the deflection is just from that base bending. So the next thing I tried was to get a big old piece of aluminum that's 2.5 inch by 6 inch by 20 inch block of aluminum. It's about $120, and it weighs about 35 pounds. And I just bolted it to that in 3 places. So now the base is sitting on that, and it actually made a lot of difference in terms of the finish quality. So this is that same cut as before. It still sounds like kind of not great, but and you can see the handle like bouncing around of the vise a lot. That's just the handle's just loosely on there, so it doesn't matter that it's vibrating, but it shows the vibrations. So it's kind of like a weather vane. And so this is you can't really tell. It's just really hard to see on the video, but the finish here was actually much better. Like that kind of rolled nickels look was vastly reduced. So even though it sounds still like it's resonating a lot and causing some chatter, it at least did improve a lot the finish. The video here, again, this is hard to see. And you can still see some of that like kind of rolled nickel look and imperfections in the finish, certainly, but it's a lot better than it was. So another thing I tried to test was like, hey, well, what if I instead of trying to deflect the column and focus on the column, what if I try to move the table itself? And I definitely saw that, yeah, even just a light touches on the table is causing a really significant amount of deflection there. So that's again like 10,000ths of deflection with just me kind of lightly pushing on the table. And I think that's all down to just those nylon roller bearings. They're kind of cantilevered out of this 1/4 inch-ish piece of aluminum that's just not rigid enough. So what I did is, since I had good luck with the linear rails before, I added the same things again onto the X and Y axes. So here is the upgrade in progress on the Y axis with the and then this time also I created 1/2 inch aluminum plates to mount the X axis on top of, to avoid any kind of flexing from that. Here's the X axis now. And then finally, the final fixture plate. Just to talk about that a little bit, I created a bunch of extra holes, drilled and tapped a lot of extra holes here in patterns so that I could mount a few different types of vices, or mount vices in a few different patterns. If you look at milling machines, they usually have T-slot tables, which have some useful advantages, but also there's an advantage to having some fixture plates. So sometimes on CNC machines, you'll just see big plates with a bunch of holes in it. And then here's the fully upgraded thing where I created a little bit larger bellows to cover the rails and stop chips from getting there. So if you listen to this, it finally sounds fine. Like, it sounds much better. It just sounds like cutting, which is what you want to hear. And you can see the handle on the vise isn't bouncing around all over the place anymore. It's happening especially a lot previously on a certain axis, like especially cutting on the y-axis, and that doesn't seem to be a problem anymore. And with a 1/4 inch end mill, or sorry, an 1/8 inch end mill, it just is like butter now. This is still a similar cut, but you can really see like, oh wow, this is not struggling in any way. Like, even with these helical ramps down into the material, it's just no problem. And then here's what, just for reference, when I'm doing facing, like if I'm squaring up some stock, I'll do this cut, which is it's a 1/4 inch ML, about 50% width of cut, and 30,000ths depth, just to show what this looks like and sounds like. And so doing this gave me the confidence to try even a little bit deeper cuts, and so I did do some cuts at 75,000ths depth of cut. I could probably push this further, but I like to keep it sounding nice, and so I haven't pushed it as far as I can go yet. And this would have taken a lot longer if I wouldn't have been able to push this axial depth up this high. With the original machine, I was running at like 1/3 or so of this depth, so 3 times as long, and it still took quite a while to get all the way through. The other thing I did is just I included this video just so I could show like kind of my general setup here. I've got the electronics off outside of the enclosure in that little plywood box. Got the laptop there. Actually just use a number pad that's hooked up to the laptop to use for jogging the machine around. And then WD-40 I use occasionally to spritz in. Does great with aluminum. I guess it's just basically kerosene, and kerosene is apparently a really good cutting fluid for aluminum. And just to show off some parts here that I've made, this is a new bearing block I created that holds a bearing. I just have spotted the holes here. That's why you see just little divots in some spots, and then I go through with the drill press and finish them. Drilling with the MiniMill is not great because the router doesn't run very slowly, and if you want to use a twist drills are really good at drilling holes. You have to run them at a much slower RPM, so I just have a cheapo drill press that I got for like $70 with Prime shipping off of Amazon, and that's worked just fine for the kind of light duty I need. So I just spot these so that I can accurately find that hole and locate that hole and drill it in the correct spot later on the drill press. This also just shows, like, this is one of the first parts where I actually spent a lot of time like chamfering all of the edges down and facing all the sides in kind of a nice way, taking nice finish cuts so it could kind of show off the finish. But still, you know, compared to a real CNC machine isn't great. But this thing weighs, again, it now weighs like 50 pounds, so it's not a 2,000 pound machine by any means. And then here's showing a smaller part. This is just a little angle bracket, like the kind of angle brackets that come with the kit or that you can buy on OpenBuilds. I just think it's a cool looking part because of those interiors look pretty neat. I was also able to actually get a pretty good finish on it. Better than I was expecting. I don't know. So overall, I mean, this is an interesting machine. It really isn't a mill. It's more of a CNC router with a 5" by 5" working area. And so a lot of people will start with this mill and build it into a CB machine because they quickly realize that, like, oh, I need more space. So there's the option to go down that route, or you could just get a CB machine to start with, or one of the other lead screw machines that are pretty good at cutting aluminum. Another route that a lot of people go is to just buy a real mill, like this Grizzly Geo704 is one that a lot of people use, and then use the mill itself to build the parts necessary to convert that to CNC. If I would have known starting out that I would be interested in machining, more interested than in routing, I should have probably just saved up and bought one of these and then worked on converting that to CNC. But the thing that was nice about the OpenBuilds MiniMill is that it allowed me to figure out what I wanted to do at a pretty cheap price without having to spend the money in the beginning to realize I was interested in it. So overall on the MiniMill, again, I think the way you have to think about this is as a CNC router with a 5" by 5" working area. And if that's something that is useful to you, you should get it. But I think there are a lot of people who would rather have a larger working area and would be better served by just getting a CNC router that's larger size. The thing that's attractive about it is it's also one of their least expensive kits. So if you want a cheap kit, or you don't have the money and you're okay with working in this smaller area, 5 by 5 even is kind of pushing it, because a lot of times you need to have some additional work holding. You need to have things that are holding down the table or holding down your workpiece. That's going to be taking up more of that 5 inches. So really you're talking about maybe 3 inches by 3 inches of like well held down stuff. So I don't know. It's very small, and there's probably some like micro machining application I'm not thinking about that would be cool. Certainly etching PCBs works great. I think it's a really cool machine to get started and into this, but I think really quickly people are going to outgrow it and are going to want something else. So it's, you know, what is the value to you of spending a small amount of money now to just kind of figure out what you want, and then using these pieces to build it into something that you decide you want after this initial investment, versus just, if you already know what you want, go buy the thing you want or save up for the thing you want, in my opinion. That's it.